Hello and welcome everyone to today's SCMH webinar. Our focus topic of the day is design risk analysis. Before we get started, it will help with the bandwidth if you close your other applications. And please feel free to ask questions throughout the presentation by noting them in the Q&A section or the chat box. And make a slide reference number if possible to help the panelists answer your questions. My name is Susan Parsons and I work for the IAQG and I'm the project manager for the SCMH. We have two panelists joining today and I'll let them introduce themselves in just a minute. We have quite a bit of materials to go over today, so we're going to get started really quick. For those of you not familiar with the SCMH, you can get to it by going to the IAQG.org, as seen here, and learn more about the SCMH. Today's webinar will be published in the SCMH, both the presentation and the recording, and you can find it by going to the IAQG or scmh.org and clicking on SCMH topics. This one will be under Plan and Manage. You'll see across the top the Plan and Manage section. Go down to 2.8 Design Risk Analysis, and you'll see the webinar posted there, along with all the guidance material we will be covering today. The webinar content today is going to be the design risk analysis shared with you by the panelists, and then followed by a live Q&A with a little more about the SCMH if we have time at the end. Steve and Soren, would you like to introduce yourselves?
Thank you, Sue. Good morning, good afternoon, good evening, everyone. My name is Steve Finnup. I work for GE Aerospace. Today, Soren and I are going to introduce you to the new Guidance for Design Risk Analysis, which was published recently in the IAQG SCMH in section 2.8, as Sue described. To introduce myself, I've been an engineer in aerospace and automotive for over 25 years. For the last 20 years, my focus has been on reliability, maintainability, and safety. I'm a member of the AS 9145 writing and deployment teams and led the Design Risk Analysis Working Group. I was also the co-presenter of the previous two Design Risk Analysis webinars in 2018 and 2019, along with Brian Gracias. Soren, please introduce yourself.
Hello, everyone. My name is Søren Knut. I work for GKN Aerospace Engines, Sweden. As Steve, I have also a background from both aerospace and automotive for over 25 years, as well as a focus on risk management, Six Sigma, reliability, and robust design within aerospace for more than 15 years. I got inspired by the work Steve and Brian Gracias presented on design risk analysis work practice less than 5 years ago. And at that time, there was not a guidance document available.
Thank you, Soren. For this presentation, I will provide the DRA concepts and guidance, and Soren will walk through the examples. The specific objectives today are listed here. Soren and I will introduce the Design Risk Analysis Callout 9145 and the new Guidance for Design Risk Analysis published in the Supply Chain Management Handbook, or SCMH. We will introduce an approach with a set of methods and tools to help a design responsible organization execute the 9145 APQP requirement for design risk analysis, or DRA for short. And we will introduce the guidance for DRA and how the guidance is formatted. Our agenda will introduce DRA within APQP for aerospace. We will define design risk and also design risk analysis and how the DRA fits within an organization's risk management process. We will introduce the DRA process and framework, including how it aligns with the 9145 requirement for special requirements, critical items, and key characteristics. We will provide an overview of the guidance, how it is formatted. We will provide some brief examples, and we'll finish up with a summary. We will allow some time for questions. Some of you may have attended the previous DRA webinar presented in 2019 or have seen the webinar recorded. This updated webinar is a result of 2 years of work by an industry working group consisting of representatives from multiple aerospace companies with the goal of providing clear guidance on how an organization may implement DRA to meet the AS 9145 requirement. That work resulted in the Guidance for Design Risk Analysis in Section 2.8 of the SCMH. So you are here. This is where design risk analysis fits within the overall product development and APQP process. Now consider for a moment the downstream elements from design risk analysis in phases 3 and 4 shown in green. You can think of those elements as manufacturing process risk analysis. Now within APQP in 9145, there is no equivalent structure for understanding and mitigating design risks. The published guidance is meant to really address that gap. Now here are the specific phase 2 activities and requirements per the 9145 standard. Note that design risk analysis is a required element and it is a PPAP deliverable. Also note that this webinar does not cover the other requirements of phase 2. It is just only focused on DRA. APQP originated in the automotive industry, in which design failure modes and effects analysis, or DFMEA, was the singular tool for design risk analysis. When APQP was adopted by aerospace, it was recognized that there are additional design risk tools which can be applied to ensure that safety, reliability, and quality of aerospace products. Therefore, within 9145, the requirement was expanded from DFMEA to design risk analysis. However, the standard does not provide any information on what design risk analysis is. Previously, we were provided 2 webinars, one in 2018 with an update in 2019, which introduced the concept of DRA. But the 9145 industry committee recognized that more guidance was needed. Therefore, a working group of experts was formed to create the guidance for the DRA, which is now in the SCMH. The resulting guidance provides a framework for how an organization can implement DRA. So what is a design risk? This is generically defined as the potential for a design to fail to satisfy the product requirements. For example, fail to satisfy product performance, durability, manufacturability, maintainability, repairability, and cost. Imagine this blue area is your organization's knowledge space. That is everything you know about designing, and producing, and supporting a product. The green box is the design space. That is everything the intended product is to do to meet customer and stakeholder expectations. Design risks are the unknowns which stem from the overlap between knowledge space and design space. You have the unknown unknowns, which are the unknown parameters representing new or unique design space, which are beyond the frontiers of your knowledge space. So you have not been here before. You also have the known unknowns, which are the known parameters with difficult regions or at the edges of your current knowledge space. It is the frontier of your product capabilities. You also have the unknown knowns. These are the forgotten or unused knowledge space, lessons learned not applied, or standard processes not followed. Now, it is also possible to have known knowns. They're not showing here, but the known knowns are when the design space is completely contained within your knowledge space with no gaps. You have mature technology and you're high on the learning curve. Now, some additional considerations are uncertainty, where you have low confidence in what you know, and variation, the tendency for things to vary the random change in the output or result of a system or a process. So now that we have a better understanding of design risk, what is design risk analysis? Shown here is the definition of DRA, which will be in the upcoming revision of 9145, currently going into ballot. DRA is a means to uncover the unknowns and take action to mitigate those within a design. The basic objective of DRA is to ensure rigorous and thorough exploration of the knowledge and design spaces to support the identification, mitigation, and management of design risks, and provide accurate and timely flow down of product critical items and product key characteristics to the next phases of APQP. Now, I do want to note that the aerospace safety assessment process, and you can reference ARP 4761, is an independent process from DRA. However, the safety assessment process does interact with the DRA process and is a key means of identifying design risks. You have the failure modes, effects, and criticality analysis, or FAMICA. You have functional hazard analysis, fault tree analysis, common mode analysis, etc., which are all tools within the safety assessment process. And any of those tools may be used to identify design risk. The safety assessment process will also inform the criticality of design risks identified throughout the DRA. Now, when to perform DRA? Consider this curve where the design freedoms decrease over the design life of a product. Conversely, your knowledge space increases over time. Therefore, the goal is to increase knowledge as fast as possible to take advantage of the available design freedom. So as discussed previously, design risks originate from gaps between the knowledge space and the design space. These gaps are greatest at the start of a project and are reduced over time as knowledge increases. Additionally, design freedoms are greatest at the start of a project and decrease over time. Therefore, the greatest benefit can be realized by reducing these knowledge gaps as quickly as possible at the start of product development. The greatest opportunity to identify design risks is with the concept design. This enables design risk analysis findings and actions to be included as part of project planning. Therefore, the DRA should start as soon as possible. Now, as the design matures and changes, the DRA is updated to identify and address any new design risks. Then as a new product is moving into production, the DRA is finalized at transition to production as a deliverable as part of the production part approval process, or PPAP. However, the DRA is considered a living document and is updated throughout the product lifecycle as any new design changes are introduced. The updated DRA can then be used as a starting point for the next project to ensure that these known design risks are addressed in new projects as lessons learned. Now, DRA fits within an organization's overall risk management process with a focus on the risk within a product design. So unlike project risk management, which typically focus on impacts to project cost and schedule, the DRA focuses on risks to product performance, durability, manufacturability, maintainability, repairability, etc. Therefore, the DRA process exists at a level below the traditional project risk management process. However, design risks that are not mitigated through the DRA process can be escalated to the project risk management process. Now, the intent of the DRA process is to identify and mitigate design risks as completely as possible. To accomplish this, the DRA process follows the basic risk management planning steps of planning, identification, assessment, action planning, monitoring, and reporting. I do want to note that this presentation focuses on design risk. Per 9145, there's also a risk analysis of the sourcing plan and the manufacturing process risk analysis in addition to design risk analysis. This slide shows the DRA process aligned to the basic risk management process steps. The DRA process provides the framework to which an organization can evaluate all their standard design risk tools and methodologies to determine where they can be applied in the DRA process. The framework also will enable an organization to identify any gaps within their current DRA process. That is, if there's no existing tool within a specific step. Now, within the guidance for design risk analysis, in Appendix A, we have provided a list of recommended tools. Here is the DRA framework with the flow between steps listed, which will help organizations evaluate their existing design risk tools to determine how they fit within a framework and if there are any gaps. The guidance provides a list of focus questions for each step, which can help assess the proper tool to apply. Now, we noted at the beginning of the presentation that the DFMIA remains a core tool within the DRA. The DFMIA methodology inherently includes the steps defined above with steps 2, 3, and 4 as part of the standard DFMIA template. Therefore, the DFMIA is not only a recommended DRA tool, but also provides a means to record and report all DRA activity to enable consistency in reviewing the DRA as an APQP and a PPAP deliverable. Now, the framework also highlights outputs, including the list of product critical items and key characteristics, which are then inputs in the manufacturing risk analysis. Now, as shown on the previous slide, one of the outputs of DRA is a communication of critical items, or CIs, and key characteristics, or KCs, to the PFMIA for evaluation for process CIs and KCs. One of the 945 requirements is to identify special requirements, or SRs, CIs, and KCs. The DRA plays a vital role in the identification of these from both the customer as well as those identified specific to the product design. CIs and KCs identified during the DRA form a special kind of design risk. If they remain in the design as a product CI or KC, there will be lifecycle cost impact to actively manage these over the life of the product. If these design risks can be mitigated or eliminated by changing the design, that will have a positive impact on product lifecycle costs. Now, during DRA Step 1, all known customer and internal special requirements, CIs and KCs, are identified and become input into the DRA process. In Step 2, the design risk identification tools will identify any additional SRs, CIs, and KCs as the customer internal ones are cascaded down through the design, and the applied DRA tools identify areas where, if unmitigated, the design risk will require specific actions to manage over the product lifecycle. In Step 3, the CIs and KCs are assessed for mitigating actions. In Step 4, the mitigating actions are worked to eliminate the CIs and KCs or reduce the risk. This step may require multiple iterations to appropriately optimize the design. In Step 5, any remaining CIs and KCs are transferred to the PFMIA to determine the appropriate process controls to manage these over the product lifecycle. Or they're flown down to the supply chain, the suppliers, as appropriate. It's important to note that all SRs, CIs, and KCs be managed with specific designations to enable traceability throughout all DRA and the applicable APQP tools, such as the PFMIA and the control plan. Now, I do want to note that there is currently not a consistent methodology for identifying special requirements, critical items, and key characteristics within the aerospace industry. There is, however, a special characteristics industry working group that is chartered with creating the standard process. The DRA guidance currently aligns to the current definition within 9145, but the guidance will be updated when this working group completes their work. So the DRA is a PPAP deliverable. When it is ready for PPAP submission, the DFMIA is the record of the results but it's also necessary to describe the methodology implemented and to summarize the results. This will enable an efficient PPAP submittal, review, and approval. Appendix C describes the reporting methodology. So I'm now going to describe the guidance document published in the SCMH section 2.8 and linked from section 7.2.18, the APQP section. The main body of the guidance is very similar to the SCMH APQP manual. It's focused on introducing the DRA and the process framework. The appendices are set up to be similar to the element cards in the APQP manual. I'll provide an overview of the appendices in just a minute. Now note that the appendices are specifically set up to be improved over time. Therefore, we are requesting member organizations to contribute tools, descriptions, or other appendices to the guidance. So the expectation is that that proposal from the member companies includes both a draft of the proposed content along with the recommendation. Now here's a list of the appendices. Appendix A provides a high-level description of the recommended DRA tools. These are equivalent to the APQP manual element cards, and I'll show these tools in just a second. Appendix B compares and describes the DFMIA, the PFMIA, and the FMICA. This is an expansion of the previous SCMH section 7.2.18, which was the DFMIA, PFMIA, FMICA comparison guidance document. Now, since that document has been incorporated into the guidance for design risk analysis, it now is superseded by the design risk analysis guidance in section 7.2.18. Appendix C describes how to capture DRA activity in the DFMIA format and provides guidance for reporting. Appendix D provides guidance on how the recommended tools can interact with the DFMIA. Appendix E describes the example problems used to support Appendix A recommended tools. Appendix F describes the importance of considering human factors in DRA and provides an example. Appendix G highlights how DRA should be considered in a computer-aided engineering world where automation is used, and it highlights that critical thinking is still needed. And finally, Appendix H clarifies how design for Six Sigma is used as a design risk mitigation and improvement. Now within Appendix A, there is that list of recommended DRA tools. It's recognized that these are not the only tools, and this list can be expanded in the future with input from industry members. Now, Appendix A only provides an introduction to each tool. The team recognized that it would be impossible to provide any significant detail on each tool without this guidance becoming a textbook. So each section in the tools list provides a very high-level introduction, a methodology description, CI and KC identification guidance, typical inputs and outputs, and references. The DFMIA is purposely mentioned first as a primary DRA tool. Now again, the goal is to introduce organizations to these tools, not to train them in their use, and the hope is that we will expand this list with additional tools recommended by member companies in the future. Now, before we move into some examples, I did want to reemphasize that the DRA framework allows an organization to identify the tools that work best for their products and processes. However, the DFMIA template remains core to the DRA framework, and you will find that the DRA tools will enable aspects of the DFMIA template. In Appendix C of this guidance, we have provided a matrix which highlights how the different DRA tools interact with the different columns of the DFMIA. So with that, I'm going to turn it over to Soren to walk through some of the tools and examples.
Thank you, Steve. Before we go to example 1, I want us to reflect on that as the input to a DFMIA analysis, it is possible to address tools for almost every column. The idea of addressing a DRA tool is to bring structure as well as knowledge to the DFMA work. Since the DFMA is a team activity, it is important to do preparation work as well as doing analysis work as predictive outcome related to different failure modes individually. Example 1 is the fuel air bracket used as one of the DFMA examples from section 7.2.19 in the SCMH. The fuel air bracket gray part consists of an adapter to the airline, the blue part, and connected blue fuel tube, the dark brown part. Brown is as well the support that the bracket is connected to by two fasteners. To start with, the systems analysis is properly done by showing a block diagram on how the different parts in the design are connected to each other. As you can see in the block diagram, to the right is the fuel air bracket directly connected to fasteners and support. On the left-hand side, and there are separate connections to airline adapter and fuel tube. Alternative way to describe a product is by a boundary diagram, where the relation of the parts are rather shown by the flows acting on the components and parts, as well as the physical connection. Functions can also be introduced and related to in the boundary diagram. The last type of diagram introduced here is the function tree diagram. Here, the product function is broken down in steps or levels that can be discussed in terms of primary function, first level, main function, and secondary function, the second level, or additional functionality. And all these diagrams are showing how the fuel air bracket is set up in our example 1. Next, by the tools just shown, we can start filling in the FMEA template with an item structure and a function structure that is related to the technical requirements. When describing the potential failure mode, it is good to think in terms of failure functioning or anti-functioning. That means no function, loss of function, degraded function, and unexpected function. The tool QFD is mentioned, and this is a classical quality tool that can be used when deriving relation between technical specification and customer requirements, but also product characteristics. See guidance document for more details. Important to reflect on when filling in these two failure modes shown is the high severity experienced for the fuel tube failure mode due to a risk of fuel leak which could lead to fire or explosion. This will demand elaborated analysis and testing to get safe installation. A zoom into the FMEA template show a more detailed description of the failure mode. The first failure mode, this example would result in a design change to how the bracket is fastened to the support that we will show on the next slide. Here we will run a variation simulation on the geometry variation with assessed tolerances. The second failure mode, this is an example where the analysis showed that the fuel tube hole diameter must be maintained within a very specific tolerance. Since this is a safety critical severity, this was classified as a critical characteristic. Note that when working with classification listing of CIs and KCs, it will start with preliminary listing And when completing the actions and updating of the RPN, this may lead to eliminating CIKCs when maturing design solution. Next, we comment the first failure mode and the need for variation simulation. To illustrate how variation can be studied, we have added an example of how sensitivity can play a role in the mounting of an assembly. In the left figure, it can be seen that the bracket to the left is fixated only by the fasteners. The bracket to the right is fixated by moving the bracket towards the right-hand wall and then fixated by the fasteners. In the figure to the right, it can be seen that the latter fixation is to prefer, the right-hand colored figure, and it can be easily seen how the color on the fuel pipe shifts from red to yellow when going from reference system 1 to reference system 2. The variation sensitivity study performed here we call geometry assurance analysis. This is a visual attractive solution to present important data analysis. Our second example is another bracket example that is shown and that is modeled as a beam. Traditionally, we can use handbook calculation to solve this problem. Illustrated here is how conflicts can appear in fulfillment of the worst case requirement. At nominal, the bracket meets the yield and ultimate stress, but when worst case assumption is included, the stresses are exceeded. Next, we want to introduce variation simulation by Monte Carlo, that is the variation view on showing design margins. Monte Carlo simulation is a relatively simple technique to determine the impact of variation on outputs due to variation in the inputs via a model or a transfer function of the relationship. When performing this design risk analysis, an important aim is to quantify risk. The quantification also is necessary in order to compare design alternatives and take good decisions. In example, you can see 4 different normal distributions where likely outcomes are picked from by using a transfer function, also sometimes called meta models or surrogate models. The functional outcome response can be simulated and a distribution of the outcome can be simulated. From the response values, the parameters can then be adjusted to get in a good agreement with the technical requirement. In our example 2, we introduce 4 distributions of our parameters that vary. This means that instead of using the extreme values, we determine a standard deviation for each parameter and assess a normal distribution. By this, we can run a Monte Carlo simulation on the max bending stress formula. The resulting distribution you can see in the figure E11 to the left. And to the right, you can see a sensitivity analysis where it can be seen that h, the height parameter, is the dominating parameter. This parameter we address further to the manufacturing team and the drawings to be a KC, where further studies on tolerance, outcome, and variation has to be handled. By reducing parameter h, tolerance band, by half, and at the same time loosen up the tolerance band of b, especially the criteria on ultimate stress margin, can be fulfilled. This is shown in table in column iteration 1 probability of failure, where the ultimate stress margin is now at the limit of 0%. And that means no cases or outcome have been calculated above this limit. This will be the main conclusion for this problem, number 2. Before we are completely finished with example 2, we want to add a third perspective on these calculations. Most likely, this is a finite element problem that is going to be solved. As initial starting point, it helps identifying the problem and the parameters that has actually to be solved and designed. A good support is to use a mapping tool. In guidance document, there are 2 methods mentioned. Decision mapping, which is a method that addresses important design decisions that has to be done at a certain stage, and that is driving the analysis work that is shown on the left-hand side. An alternative can be found on the right-hand side, a parameter diagram or P-diagram. This is a method that highlights the functional relationship that has to be investigated. Control factors are the factors designed, and noise factors are the factors you cannot design, but that you have to consider the influence and robustness too. In our example, you can see that tolerances can be viewed on each side. In this P-diagram, we have chosen to put them on the noise factor side. Other example of noise can be excessive loads and temperature, like heat temperature and extreme load paths. When you know what parameters to vary and what response to optimize, you have also a perfect setup for running a design of experiments. Design of experiments is a perfect way to gain knowledge on your functional response. Design of experiments is a well-established method to study a design problem in order to find a functional relation between the design parameters and the functional performance value. Whenever a design problem is set up, a knowledge space has to be explored. As mentioned by Steve in the beginning, see page 13. Design of experiments is a proper way to do this exploration. In the example shown, a factorial description is shown that leads to a transfer function, a meta model, described in terms of polynomial function. When doing calculations nowadays, schemes like a space-filling Latin hypercube sampling designs are used that also allows for other functional expressions and meta modeling. To end example 2, we show how a design of experiments can be used to explore the knowledge base and to get a meta model that can be used for Monte Carlo simulations. The identified factors are set up in a test plan according to a full factorial design of experiments. In the rightmost column are the calculated response values to simulate a typical finite element simulation. By evaluating the response, we can estimate a meta model for the max bending stress. With the meta model previously shown, results can be as well simulated by Monte Carlo. While doing this, we will end up with the same values as previously have been shown. And this was all I wanted to present. And now over to you, Steve, for a wrap up.
Thank you, Soren. So let's wrap up this webinar. Only a few more slides remain. In summary, design risk analysis is a 9145 requirement and a PPAP deliverable. The guidance for design risk analysis in the SCMH, section 7.2 and 7.2.18 provides the framework for your organization to evaluate how your existing design risk tools enable the DRA and if there are any gaps. The DFMIA template can be used to record the DRA activity, and the guidance defines how to report on the DRA activity. This is defined to ensure a consistent reporting means, which in turn will support an efficient review as part of PPAP approval. Appendix A of the guidance provides a recommended list of DRA tools, but this is by no means a complete list. Our goal is to continue to expand this list with the help of contributions from the member companies. Now with that, we will turn it over for live Q&A.
Thank you, Steve. Thank you, Soren. So let's start with some questions. I think I'll take the first one. Hello, will the PowerPoint be sent after? Well, we're not going to send it to everybody, but it will be published, and we will also publish the recording. Many people are asking if it's going to be recorded. Yes, it was. And it'll take about a week or two, and then we will publish the presentation along with the recording. And I'll show you where at the end of this presentation. Okay, for the first question, back on slide 20, there was a question coming in, or more of a statement, presumably. A design is created in between step 1 and step 2. Can you take that one?
So yes, and maybe slide 18 is a better slide to talk to this question. So the question seems to be, when is the design created in relation to the DRA process? Now, the way I look at this is that the DRA starts with the concept design. Therefore, as soon as you have an understanding of what the design is going to look like, you can start evaluating the risks. And so by applying various models, you can begin evaluating the concept design. So with tools like parameter diagram or boundary diagram, you can start characterizing what the design looks like, and then what are the potential design risks and how to begin planning to address those risks. Now, having said that, from a supplier perspective, sort of for a supplier who has design authority, the DRA can start with the requirements review. What requirements, if not met, will result in a safety impact or an operational impact or some other criteria deemed critical or important. Those requirements can then be evaluated as part of the DRA to help guide the design risk in mitigating those risks.
Thank you. Any time frame available when this mentioned working group will be done with creating of the guidance to define CI and KCs? For that one, I'm going to combine the next two questions since they are about defining critical items and critical characteristics with examples. Any time frame for what this mentioned working group will be ready with the guidance to define them? The SCMH Special Characteristics Definition Project Team has been working for some time to define and agree on the terms. You can imagine that agreeing on these, something like this, takes time and debate. We are looking at the end of the year to have this published. The timeline can move a little, so we need to be flexible. Do you want to add anything to that, Steve?
So I'm going to defer to the Special Characteristics Project Group about that. I will say, similar to design risk analysis, defining a standard process for CI and KC definition management, it's a big topic. There's not a clear standard methodology across member companies, so the working group's charter is really to bring together all the experience from all those member companies and define one standard methodology that we can all use, and that's going to take a little bit of time.
SR appears on the slide before guidance for design risk analysis to be identified, but then they do not appear again. What do we do with SRs?
The special requirements are defined as those that are having a high risk of not being met. So by definition, if you have a special requirement, you have a design risk. Therefore, you work those special requirements through your design risk analysis process. Now, special requirements may or may not also be defined as a CI or a KC, but they are definitely a design risk that has to be considered.
Where can we find these appendices?
So they are in the guidance for design risk analysis in the SCMH. So you'll go to section 2.8 of the SCMH, which is the design risk analysis section. You'll find the guidance for design risk analysis document. You download that document and the appendices are within that document.
Thank you. How can software be integrated in a DFMEA? What would be your recommendation? Via System FMEA, which integrates, for example, DFMEA plus Software FMEA plus Mechanical FMEA and Cyber Security FMEA.
So I will say from a software perspective that APQP per 9145 and the supporting information in the SCMH tends to be focused on the mechanical and hardware aspects of the design. I don't believe that as an industry, we have really standardized an approach on how software is addressed from an APQP standpoint. However, from a design risk perspective, we can look at the software and specifically the interfaces between software and hardware and evaluate if there's any risk there. Now, I will say that there is a IEEE standard 1633-2016, which does contain a process for conducting a software FMEA, but this has not yet been evaluated by the 9145 deployment team.
Steve, just a short comment from me, Soren. Firstly, Appendix G comment shortly on the model-based design approach and the software in the loop that is into the simulation of functionality. And secondly, in Appendix F, we have the DRA and human factors that actually also handle this type of interface problems that we actually can experience. In this section, methods like functional hazard analysis and fault tree analysis are discussed in order to identify interface risks. I would consider also the software in these analysis methods. Therefore, we have some reflections on how to deal with situations where the problems are not just mechanical in this guidance document, but of course, this important extension is a topic that has to be explored even more by the DRA team. Anyone who knows something more about this topic is very welcome to contact the DRA team.
Thank you, Soren.
Okay, thank you. When you have a KC and you mitigate it with the actions taken in the DFMEA or with other DRA tools, how do you identify that this is no longer a KC? Do you remove it from the DFMEA form, KC column, in parentheses, SCMH 7.2.10 DFMEA template classification column? Or do you indicate in the KC traceability form, SCMH 7216, that this was identified as a KC but is no longer a KC in any field of the traceability form?
So this is a great question. My personal preference is that you eliminate a CI or KC through the design risk analysis process. And instead of deleting the CI or KC reference, you strike through it to indicate that the CI or KC has been addressed and eliminated. And you also have notes to explain how it was eliminated. In the second example that Soren gave, both the H and B parameters were initially listed as KCs, but the B parameter was eliminated. Therefore, it could just be struck through with notes on how it was eliminated. Now, it's also very valuable to use the KC traceability form, which is located in the SCMH in section 7.2. Use that as your record of CIs and KCs and note the justification on why it was eliminated. Therefore, if the design changes in the future, this becomes a really valuable historical record to ensure that you are not reintroducing a CI or KC that was previously eliminated.
Thank you. Is DRA only applied to new products, or can it be used for legacy products as well?
So yeah, DRA is definitely applied to new products. But when it comes to legacy products, you gain value by doing a DRA analysis. If there's a design change to a legacy product, the value is gained by focusing on the changed elements of the design. My recommendation is not to apply DRA to the parts of the design that are not impacted by the design change, as the value is going to be very minimal. Therefore, if you have an existing design, you're making a design change, I would definitely do a DRA to evaluate that change. As I've mentioned before, the DRA will then be a record of design changes and the design risk, and you can use the DRA when you start a new project or a new product development as input as lessons learned. In theory, every time you do a product development, you should get a little bit faster at it by having this historical information.
Okay, and this next question is more of a statement. So the output of the DRA have to be KC, CI, or SR, and the related justification. Is this operation also part of the DRA if only safe operation is done as DRA? Is DRA considered complete? Can it be notifying?
Ultimately, the output of the DRA is an optimized design. So all identified design risks have been addressed by the DRA. These design risks will contain multiple factors, including safety and performance, operational impacts such as dispatch and mission reliability, and other aspects deemed important to the performance of the aircraft. One of the goals of the DRA is to treat potential CIs and KCs as design risks, and work to minimize those in the final design. Ultimately, any remaining product CIs and KCs are then input in the manufacturing risk analysis process, for example, the PFMEA, to address how to manage those product CIs and KCs through process. The reason to eliminate many product CIs and KCs through the design change is that there's cost to manage the remaining ones over the life cycle of the product.
Okay, and this is the last question before we wrap. Legacy design risk can use the impact analysis step of the change control process.
The part of change pack analysis is assessing the impact of any planned design changes. Therefore, a change impact analysis can be considered a design risk analysis tool. Now, you will want to make sure that the change impact analysis is focused on the technical design risks of the product rather than any programmatic risks. And those risks should be documented in the DFMEA format as the DRA becomes the means to capture those lessons learned. That is, what issues drove the need for the design change. And the DRA can then be used, again, as lessons learned for the next project.
Steve, I want also to comment on this. We have in the guidance the design review based on failure mode, DRBFM in Appendix A15, as a tool that is a variant of DFMEA, but it handles only changes of a product design in a structured way and can be used in a review of a design, as the name say. I would say that this can be an appropriate way of performing change impact analysis in an FMEA format. That's all.
Well, thank you. This concludes the Q&A portion of the webinar. If we did not answer all of your questions, or if you have more questions after, you can just use the Contact SCMH link in the SCMH as shown in the next couple slides. Steve, can you go to the next slide? And put it back on full screen, probably. So next slide, please, on full screen. Thank you. So this is the, just to show you where you can go and click on the IAQG and the SCMH Contact Us. You can even take a survey and provide even further feedback for us. Next slide. Next slide, please.
A little bit of a delay.
Yeah. Okay. We're still waiting for the next slide. There it is. So this one just shows where to find the recordings. For example, the recordings for APQP are listed under the APQP 7.2 section, and it shows webinars right above the core guidance and toolbox. This will be the same thing that we do in the 2.8 section. Next, please. This is where you can see all the webinars that we have currently identified and posted in the SCMH, Advanced Product Quality Planning, Acceptance Authority Media, Business Continuity, Work Transfer, Competency Management, Data Science and Artificial Intelligence, and the next one will be Design Risk Analysis listed on this slide. The next one. If you want to get a little bit of an advance warning or notification when a webinar will occur, you can click on the announcement page once in a while and you'll see an upcoming date or webinar. And then you'll also have an opportunity to register long before others get the newsletter, or within a couple days anyway. The next slide. This shows the search function and the About SCMH. Just wanted to point that out because About SCMH explains a lot of details with a communication pack, an alphabetical listing of everything that's in it, what's new and what's been the latest items. It'll pop up there for the recording. It'll show that it's under what's new, and you'll be able to see it right away by going and checking that once in a while. You also have the SCMH search. If you click on that search function and type in anything you want or curious about, if it happens to be advanced product quality planning or design risk, you just type that in and it'll populate a list of all the things that talk to that within the SCMH. Okay, and the next slide. That's the contact SCMH link that I was talking about. So if you had a question that didn't get answered today, or you have questions in the future about this topic or any other topic, click on that and send it to me. It'll come right to me. I will then forward it to the appropriate project lead and we'll get you a response. Next slide. Steve, would you like to close from here?
So before we leave, we would like to thank everyone for attending. We'd also like to thank everyone on the Design Risk Analysis Working Group who contributed their time and expertise through authorship and/or performing critical reviews of the guidance. So key members of the team were Philippe Cosio from Airbus, Chad Foster from GE Aerospace, Leanne Jimson from Boeing, Gurdeep Panesar from L3 Harris, Manny Rajamani from TASL, and Francesca Cesare from Leonardo. We do want to give a special nod to Brian Gracias, our founding leader and DR expert, who retired before we finished the guidance. And then also a special thank you to you, Sue. You were critical in providing guidance for the team and coordinating between our team and the IAQG. So thank you, everyone.
You're very welcome. And thank you, Steve. And thank you, Soren. Great job. Thank you all for coming today, and we'll see you at the next webinar. Have a good day.